In 12.2e, let's determine which of the several transformations does a better job. Should it be a power or it should be an exponential? I want to refer back to the linear function. So we looked at the format of linear. Remember in a power function, we said it's going to be something like squared or cubed or to the fourth. What happens when you transform that? So let me show you if we use logarithms, by the way, again. If we take the log of both of these sides, like we did for the exponential, if we take the log of both of these sides, I can pull this apart right here. When you pull it apart, for properties of logarithms, we have this on the right-hand side. Now, this p-value can actually come forward because it's an exponent. When you do that, what you should notice, if we have a power function, or like a quadratic or cubic, or a radical like a square root, what changed? If you noticed, the y's have the log and the x's have the log. So if you want to linearize any power function, all you have to do is take the log of x and the log of y. What's interesting about this, in the power function, keep in mind if this was quadratic, that p would be a 2. So what happens is this p-value actually ends up becoming the power that was original power. This is the slope. This, by definition, where the p sits on here is the actual slope of the function. So the original power of the function now literally becomes the slope. Kind of interesting. But take this away. To linearize anything that has a power function, take the log of y and the log of x. But remember, we learned in the last video, to linearize anything that has an exponential function, all you do is take the log of y. So as long as you know those two key things, you will be totally fine with the second half of chapter 12. Let's look back at the child mortality rate. Before, when we analyzed this data, we took it as the reciprocal. So we did 1 over x and 1 over y, and we analyzed it. Well, here's what they're going to ask you. This is a very common question for this type of section. Which model is this? Is this a power model or an exponential model? And all you really need to remember, folks, is for an exponential model, what we do is you come on in, you keep x, you do the log of y. If it's a power model, what they're going to do is the log of x and the log of y. And you just look to see which one gives you the best linearity. So here's what they're saying. Use an appropriate log transformation to make the association linear. What they did, notice to this data here, they kept x's the same, but then they came over here and they took the natural log of y. So you have to ask yourself, which model does this represent, power or exponential? Well, let's look at this one next, though. What they did here is they took the natural log of x and then here the natural log of y. Which model is that? Well, clearly, if you undo both of them, it's the power function. So this guy here represents the power function. And then this guy here represents an exponential function. Okay, which one's more linear? Well, if you look at it, here's my analysis. The scatter plot of the natural log of income versus the natural log of under 5, which again was right here, our natural log of x and our natural log of y, that scatter plot is more linear than the scatter plot of this function. Therefore, my answer is the power function is going to be the one that is best to use to linearize my data. Most of the problems I have seen about this topic are a question that look just like this. And it's literally as simple as just reading the scatter plot to see how the data was transformed, remembering for a power, you log on both x and y. For an exponential, you just log on the y. Continuing on, sketch the resulting scatter plot, calculate the regression line, and sketch a residual plot. Again, you're probably not going to have to do this, but here is the transformation we chose. Again, we chose that it was going to be a power model. Here's the residual of the power model. We can come up with the equation of the line from the computer output. Notice, read the regression here. It's very clear, and just read the details. They're telling us right here they did natural log of income and natural log of under 5. So that's the x and the y values. So they clearly, we can tell, they did a power model. Well, write the equation. Fine. Be careful. We're doing natural log of y hat. Here's my y-intercept and slope, and it's natural log of x. And I'm going to define those variables right here because you want to also do that. Keep them there. Fine. Let's make a prediction now. Predict child mortality for someone with the income of $41,256. Well, child mortality is, therefore that's going to give us an equation. It'll be the natural log of 41 to 56, and it's going to be equal to what we have above there, minus our slope, and then I'm going to keep it as the natural log of x. Okay, to solve that, what I'm going to do is just simplify my data. So I'm basically going to take the natural log of that value there. Now let's go ahead. I'm going to subtract 11 from both sides, and then I'm ultimately going to divide by 0.9374. So again, subtract the 11, divide by this, and here's what I'll get. Now to solve for this value here, what I can do is, this is just log base e, so I'm going to do e to this power equals x. This number right here ends up simplifying when I do this fraction is this value. So now natural log of e, log base e, so e to the power of that equals x. When you simplify this, what you're ultimately going to get that the answer is x is going to be approximately a mortality rate of 2.5. Now, if this is on a multiple choice question and you're struggling, again, you're not sure how to solve even for this, use guess and check with the various answers and you should be just fine. I do want to just go back to this example about mortality rate and income and show you some analyses I did in our calculator. I did the linear regression, just how the data sits. This is using the data without any linearization, so just x and y. Clearly a curve pattern. I ran a linear regression. Here's the equation I got. So this is if I kept it as it was and ran the linear regression. Now this next graph, what I'm going to do is show you if I thought it was an exponential pattern and I linearized. To do that, remember to linearize exponential, keep the x the same and take the log of the y's. This was the equation. Here's the line of best fit. And then the last one is our power function. So I linearized both the x and the y in this case, and I came up with a new equation. Even just looking at the scatter plot with the line of best fit kind of tucked into there, you're going to ultimately see the power function really does look like it's the best model. Really, to confirm it, what I should do then is to actually come up with a residual plot. So let's just talk about how did I graph this. Well, to graph it, what I did is I created a list. I did a new list where I took the actual natural log of all the x's in one list, and I took all the natural logs of the y's in the other list, and I did a linear regression of where this data sat, and I got the output. Now remember from chapter 3, once I run the regression, the word residual in my calculator actually stores all the residuals for this regression, so I can graph the residual. Here's how you do that. To graph the residuals, I'm going to do a stat plot, so above y equals, do second y equals or stat plot, and I'm going to click on a scatter plot. My x's of my new data, my natural log of x, by the way, was here, and I'm going to type the word residuals. And if I graph the residual plot, it looks like this. So not a lot of particular form, a lot of nice equal balanced scatter. So based on this, I am content with the power model for this scenario. Now, we've already kind of talked about this a little bit. This is called the ladder of powers, and it's not really focused on the AP exam as much. I'm yet to really see a true question about it, but I think it's important to talk about. This right here, it looks like the XY axis in that if we think about it, this way is our x's and this way is our y's. Clearly, the x's are moving upward in quadrant 1 and the y's are moving upward. So what they're going to say is if when you look at your data, if you see a pattern where it's kind of looking like this, the best way to actually transform it would be to come in and move up to your x's. You would do a bigger number on your x's. So maybe to transform a curve to linear, you would do x squared or x cubed. Also, you may do that to your y's, maybe y squared or cubed to the fourth. What if you had a pattern over here in quadrant 2? Well, in quadrant 2, the x's are getting smaller, the y's are getting larger. So what they would recommend, if it looks kind of scattered like this, move your x's down. So do a lower thing, a square root, a cube root. Move your y's up, so do y squared or y cubed or y to the fourth. It may impact it. Here's another example. What if you're in quadrant 4? In quadrant 4, if your pattern that you're looking at looks somewhat like this, which would kind of be exponential growth, what their recommendation is notice you're going x is positive and the y's are going negative. So the x's are going up, the y's are going down. So to your x's, again, maybe square them or cube them or fourth power them. To the y's, make them smaller, so square root or cube root. Ultimately, the most common questions you have about transformations is, though, it comes back, they're going to ask you if it's an exponential or a power model. I have seen them give you some like a function like when we did a equals pi r squared in a past video. To transform, to get rid of that squared, maybe I square the x's or I square root something. So they might have a connection with that. So let me know if you have any questions about the transformation concepts. And we are officially done with our notes for the entire textbook. So way to go. Let's wrap this up and start getting ready for that real AP exam and hit our review section once we finish Chapter 12 testing.